since this might be a long one anyway. Let's go ahead and get. I can see I'm recording. Did I start another recording?
Record if that's what you're looking for again.
Okay, all right. So it seems like we're already recording. Okay. All right, so where we left off was this notion of having sort of a randomized network. And what the problem with all these randomization routines is that, believe it or not, randomizing, like real randomization, is actually very difficult to do. Ova Frank had a wonderful piece on how to generate actual random networks within real constraints, and the ways in which it can go wrong is pretty high. But thankfully, we don't have to do that. We've developed a statistical framework, and this is coming out of Holland and Linhart, a model called P1 originally. And the P1 model led to a P2 model, which led to a P3 model, which led Stanley Wasserman to create this thing called the P star model, which is that it's where 1, 2, and 3 were originally a set of known effects that went into the model. The star was any effect that you could specify. So it's a generalization of these models. And the P star model is the initial instantiation of what's come to be called the exponential random graph model. Stan Wasserman has a bit of a complaint about that terminology because the class of exponential graphs is exponential random graph models is much wider than the class of P star models. And so he dislikes the substitution of the terms, but we live in a normative instantiated world. And so the institutionalization of statistical terminology has us now saying ERGMs for all of them. So that's what we're going to stick with. And I've always said ERGM. I think other people say ERGs. I don't know. I think ERGM, it's kind of a funny word, but there it is. So what I want to do is just spend just a minute. Again, we go into much greater detail in the model, in the videos. So please jump into those and grab them if you want. But the goal that I want to do is just give you an intuition for how these models work in terms of the way we specify effects and what those effects might mean. And this is for people who have no idea, who haven't seen these before and are just trying to get started. These kinds of models are fundamentally about trying to predict the observed network. So given that you have a network, the technical way that we think about this is that, remember what I said before, the inference question is a little bit different, right? So you're not in some sense, you have the population, and what you have is the observed population on the day you did your survey. But most of us believe that the graph we observe on any given day is subject to all kinds of randomness. And it's actually that there are real relationships under there that are generating some stochastic, with some kind of stochastic noise, the observed graph you see on any given day. And so the way the question gets framed is the graph that I've observed a reasonable draw from the class of all random graphs with whatever constraints I've put into it? And so that's how I like to think about these models. And the first constraint is just density. It's just the number of edges in the graph. And you're going to see that's a pretty crappy constraint. Most real world networks aren't well described as having been drawn from the distribution of all graphs with that density, right? There's a bunch of graphs that don't make any sense given what you said. And so we keep narrowing the field. And so what I want to talk about with these models is how you might do that, right? Just intellectually before we get into the technical part of how you do it programmatically. And so this is just a little toy example to help build this kind of intuition. Assume you have an observed network, like you see here in this little adjacent. Is my screen being shared? Yeah, so if everyone can see this funky little observed network. So in this case, I've color-coded it to make it a little easy for us, right? So we have observed ties are in red, observed zeros are in blue, and the diagonal is meaningless in this case. It's to be a structural zero. It's not informative for us in this particular context. And so we might want to think about this as a logit model, just for simplicity. And for those of us in social sciences, this is a common thing we've played with. And so we have some dependent variable between nodes I and j. It's a function of an intercept and a set of effects. And so what are those effects and how do we make sense of them? And so the simple way to think about this is you could build a model where yij is just equal to the intercept, right? There's just some underlying probability of a tie between two nodes. This is the density model, right? So this is telling us, and you'll notice that now the predicted value for this network is that if all I were doing were saying Yij is equal to this guy, to some intercept, it ends up being the intercept is estimated as minus 1.13. Exponentiate that, you get 0.24. That's the density of this network. And notice what it's predicting. The model's predicting a constant field. Every edge is exactly equal to every other edge. That's because there's only one parameter in this model. Right? So this model describes a world in which every edge is equally probabilistic, right, or equally probable. So this is just a random Erdos-Ranney random graph where you flip a coin is on and off 0.24, and you hit as often as you miss, right? So it's not a very well informative model. Now, you might add to that model something we could call row effects or sender effects. And so in this case, we just know that some people have different degrees than others. And so what I put down here on the edge of this matrix is you can see the out degree of each node. So this node sends one tie. So out of all the people that are there, they send one tie out of all of them that are possible. So the probability of any edge is 0.13. Whereas in this node, they spend 5 nodes. So given that there are, looks like 10 alters or 9 alters they could send to, that slightly over half are filled. And so the probability of seeing a tie in this row is necessarily higher than seeing a tie in this row. And that's the idea behind a sender effect in the network. And if you're to think about this logically, it'd be something like, say, I don't know, seniors in a high school have more friends than freshmen in a high school, say. And that would be one way to think of this. Now, note that what this does is it constrains the set of possible graphs where you have certain kinds of substitutability. So now every node that has the same out degree, they're probabilistically substitutable. So it's the case that you can see they're the same color, right? So you have the darkest blue for the 1, the light blue for the 2, goes her shades into white and then into pink and then into red on this blue, in this cool hot scale. Now, you can probably see where I'm going with this. If you can have sender effects, you could have receiver effects, right? And so it's the case that some people are more popular than others. And so it could be the case that I build into a probabilities frame those nodes that are likely to be hit versus those that are not likely to be hit. And we could do it joint. Now, if we do a joint, that gives us quite a bit of information, right? So it's the case that these are ties where people send a tie versus people receive the tie. If I have a high out degree and I'm also really popular, like our node right here, so this node receives 4 ties and this node sends 5 ties, well, that cell's really probable, right? And so we would expect to see it. And just to remind you, the bold ones are the observed ties in this network. Well, then we could add a third parameter, or how many? I'm at 4 now. So we have a 4th parameter, in which case now we have some dyadic feature. And I don't know what it could be. It could be, you know, we both love, you know, punk rock or something, right? So it could be anything. But it's some feature that's not characterized by just the sender or just the receiver. It's some characteristic that a dyad shares in common. And by virtue of sharing it in common, it makes us much more likely to be tied to each other. And this could be like having experienced something, having shared something. I'm calling it dyadic similarity because it's something that is usually a positive relationship to our outcome, right? And so this is the logic. Now this model as it's currently specified, I've deliberately called it a dyad, a sort of a dyadic regression model. This model, if all of these features in the model are not based on any graph feature, if it's not the case that we're linking to each other, then this is what we call the dyadic independence model. So we're both white, we're both black, we're both something. It's we're dyadic dependent on each other. Our difference of being tied to each other is because of some feature of our dyadic characteristic, but there's no triadic or other kind of feedback process built into the model. And so that's what's there. Now, these becomes a little more complicated when you sort of fold in the kinds of things that create similarity might be things that are dependent on the graph. So it might be that you and I are similar because we share lots of third parties in common, that we're both friends with the same people. Or it might be that you nominate me because I nominated you. That would be a reciprocity effect. And so it is possible to have what I'm calling here similarity features or dyad-specific additions to the model that are not necessarily dyadic independent, but are based on something else in the model. And so those are somewhat different. Okay, and so the nice thing about this kind of modeling framework is intuitively, that's what all of our models are going to do when we're trying to explain the graph. Is we're going to have some features that have to do with columns, some features that have to do with rows, and some features that have to do with joint probabilities of rows and columns. The trick comes in specifying what those things are and figuring out whether or not your model fit or not. The problem, of course, with this model as a logit model is that it turns out that once you've moved beyond some very simple row features and very simple column features, that the fact that these elements are not independent of each other really buggers with your probability distribution and makes it impossible to estimate properly. And so there's an estimate, not only is it a model specification difficulty, it's a model estimation difficulty, which makes things that much more difficult. And so into the breach steps this new way of thinking about networks, which is new in the sense that it builds up from a past, but has been recognized as being different, which is this notion of an exponential random graph model. So an exponential random graph model, why is my thing not working? There we go. Builds from these models called a P1 or a P2 model. And a P1 model and the P2 models were this kind of a row or column effect, but instead of having a characteristic like the degree, it literally just fit a parameter for each row and a parameter for each column. And so if you estimate these kinds of models, what you get out of the P1 model is a attractiveness coefficient and an expansiveness coefficient, which tells you how attractive a node is, right? Like what's the highest, what's the improvement in the probability of nominating that column or that row sending a tie. You literally add 2n parameters to the model. And as you might imagine, your expansiveness parameter is correlated with your out degree. Your attractiveness parameter is correlated with your in degree. The reason they're not perfectly correlated is that there's a third kind of parameter, which is reciprocity, which is that some of my out degree ties are there because I reciprocated your tie to me. And so that's why it's not a perfect correlation between in degree, out degree, because we're also controlling for reciprocity. As it turns out, just as an aside, I love this model. I love it because not for the reason that it was originally designed, it almost always shows this feature, but because it gives you a way to estimate popularity net of reciprocity. So if you want to know whether or not a node is attractive, like is generally attractive, you want to disentangle their gregariousness from their attractiveness, which you can get by separating out their reciprocity and their out degree. So that's kind of a fun way to generate a new descriptive statistic. So anyway, you have lots of these kinds of models, and you can fit them with lots of these parameters. It turns out, of course, that because of the non-independence of the errors in the observed data, you end up with standard errors that are nicely referred to as approximate, but in fact are probably not. And so how do you fix that? You fix that with this thing called an exponential random graph model. And what these models all have in common is that you're predicting, is that it just respecifies this logit model we had before in this generalized framework. And the generalized framework is that the probability of observing a network X that's from the class of all networks of that type is a function of a set of summary statistics on the graph and their parameters, right? And so Z is this network of network statistics. It could be the row sum, it could be the column sum, it could be reciprocity, right? So whatever kind of network statistic you have here is associated with a set of parameters, and that's then normalized across the set of all possible graphs with that set of parameters. The difficulty comes in with this denominator here. It ends up being in most cases impossible to specify what this denominator is exactly. But it turns out, and this was the insight that come out of the early models in the 90s, was that there's a way to think about this process conditionally. And once you think about it this way, what it effectively does is it treats the network statistics not as an observed statistic, but as the difference between the observed statistic when the tie is forced to be present versus when the tie is forced to be absent. And every other row and column and every other cell in the network is held exactly as it is. And so that's what the complement here means. It is the probability of the Xij being 1 given the rest of the graph kept exactly as it is. And when you do that little conditioning, it gives you the ability to create this statistic. And I didn't, in the rest of the slides, I have them hidden. It shows you the algebra that gets you to this point. It shows you that the thetas then here that you were trying to estimate can be estimated as a function of this difference without having to write this guy down. Effectively, what happens is the denominator of this ugly thing that's impossible to enumerate falls out when you work it out as this, and you think about it as this process of differences. What that means then is, instead of just adding in a row or column indicator in the model, say, or a row effect indicator or a column effect indicator, you need to ask yourself, what's the change statistic? Like, what does the statistic of the graph look like if I add that tie or delete that tie? Now, sometimes that is knowable just analytically. I just know what that statistic is by virtue of how it's defined. And so I can say that what's the difference if my statistic is degree? Well, if I force the tie to be there and I force the tie to not be there, the difference in the degree is going to be 1. And so that's just going to be a vector of 1s. And so all that a vector of 1s is in a logit model is an intercept. And so if your goal is to think about what these statistics mean, sometimes they're really simple. And so same thing with reciprocity. If you go through and look at the change statistic, it turns out that the thing you actually enter into the model is just an indicator for the not nominated U. So under the hood, sometimes things are really simple. Sometimes they're not. So if the global statistic you're trying to measure on is 4 cycles, or the tau statistic in a hierarchical triad model, then what you literally have to do is go through and calculate the change for each one and put that sucker in the model, and that can be really expensive and time consuming. So you want to be careful how you specify these models, but the logic is always the same.
But it's getting out of this denominator question, isn't it because it's basically simulating across the stochastic process? There's basically like, this is the world where there's the positive and negative is this is the difference, this is, and you just basically walk down this chain.
Well, I think it's one way to help you think about the interpretation. So you can think about the probability of a tie between I and J, holding all else in the world constant. If this statistic were true or not, is a way to, it tells you, it helps you think. The way I think about it intuitively, it's increasing, is whether or not this statistic is increasing the probability of a tie, then you would expect that change should be bigger in the cases where the tie is present than not. So I don't know if that's the question you asked or not.
Yes, that's the question I was asking.
Okay. So the way this is done is that you estimate the problem, of course, is you still can't do all of this mess very well with a logit. That was the original trick that Stan Wasserman and his group helped develop originally. And under a certain set of very rigorous assumptions, the estimates are correct and the standard errors are fine. But most of the time they're not, particularly for any of these kinds of features, which we call non-dyadic independence, so triad effects or other effects like that. So in those cases, you have to fit this using a simulation approach, which is called an NCMC chain, which is the part that I was alluding to before, which is the contribution of the Bayesian statistical modeling to this group. And so that's the actual under the hood estimation technique. Ends up being much more complicated than a standard logit model is for most kinds of models. And that's why the models in practice, when you do them, end up being hard to fit.
But the MCMC is getting you the denominator. That's really what the MCMC is doing for you, right?
No, I don't think so. You're never getting the denominator. It's getting you a stable solution to the theta parameter.
Well, it means you don't have to have the denominator because you're going through the stochastic process. I mean, basically gets you out of, like, you don't have to have a closed form world because you just basically.
Yeah, no, see, the thing that gets you out of having to have the numerator or the denominator, excuse me, there is this differencing. I think that is an analytically distinct question from the NCMC estimation technique, which is why Wasserman proposed the pseudo likelihood estimate in the logit, because if you were, and someone else in the room who knows the stats better than I do, I don't know if David left or if he's still here, I can't see my list of participants, but correct me if I'm wrong, but my understanding is that those are analytically separable pieces.
I agree
Okay.
with you, Jim.
Okay, thank you. Sometimes sometimes I know just enough of this to get myself into trouble. So stop me if I'm making something stupid. All right, so from a pragmatic standpoint, what do those of us poor mortals who are trying to estimate these models get out of them? The beauty is that people like Dave and Carter and and Pavel and Mark Hancock have done a lot of the work that goes into figuring out how you calculate this critter for us. And they've built these models in the StatNet package. And these packages, the package that I really encourage you to go out and find is this thing called the Exponential Random Graph Model in StatNet. It is now beautifully documented. And so the amount of detail that is in this model is in this documentation is kind of remarkable. And there's a huge number of tutorials for how to use the base model. And the new version of the models coming out is going to be even more greatly expanded. But the kind of models you can fit are intuitively those things I showed before in this first set of slides. Homophily parameters are dyadic features. So those are the birds of the feather kind of questions. And the term we use for that in the ERGM modeling thing is a thing called node match. Social balance is something like a friend of a friend is a friend. And so you would expect there that tells me that if you and I are friends and you are friends with someone else, then I'm likely to be friends with them. That's a closed triad effect. It turns out that the actual closed triad doesn't work very well, so we use this thing called the Guest, and I'll talk about that in a minute. But the point is, you can think about lots of different terms in lots of different social processes, as instantiated in patterns on the graph, and then that's the kind of thing you want to put into your model. All right. So here's that asterisk. And so that asterisk is that there is a model sensitivity problem, which is that ERGMs, this is always true, we just forget it, is that the MCMC process is a simulation model where it's trying to fit the average statistics of the graph that you've put to the set of randomly generated statistics that come out of the MCMC chain. Now, the problem with that is that it's going to do it over the sequence of the entire set of simulations that are generated in the train. And the underlying model specification is taken to be true. And true with a capital T. So when the assumption is the model is properly specified, it really means the model is properly specified. As a sociologist, like, we're crappy model specifiers, right? And that's fine because OLS is forgiving, right? And so we're used to dealing in a world where we get a positive coefficient on something and it's fine. It tells me that education produces more income. I really don't care if it gives you $1 more or $10 more. It's in the right neighborhood and that's fine. And it's a little bit of bias here, a little bit of bias there. We can usually hold our nose and live with it. If you think about something like a triadic effect in an ERGM model, what a positive coefficient that says a friend of a friend should be is good would say that the more friends of friends I have, the more friends of friends I should have, right? And so you would expect that a closed triad, if the real world says that there's a positive coefficient on social balance, then what that would say is that if this is good, if a few closed triads is good, then lots of closed triads are better. And so what that leads to is this notion of a model degeneracy. And so if you were to just put into the model for a place where there are in fact more closed triads than you'd expect by chance, because you've specified that model to say that the marginal return of each additional triad is positive, that means that the absolute best fit for this model is going to be a clique where every tie is tied to every other tie. And in order to balance out in the average the number of ties you've observed where there are cliques versus not, it's going to give you some empty graphs and some complete graphs, and the exact middle is going to be the proportion of graphs that generate the number of triads that are in your setting. And so this has been known as the model degeneracy problem. People have treated it as if it's a problem with ERGMs. It's actually a problem with your model specification of ERGMs, which is to say that the model really has to be accurately specified. And what we really mean when we think of a friend should be a friend is that we mean that most of our friends should be friends, and that the additional marginal return at some point has a decreasing slope to it. And so it ends up being the case that this thing eases into a level at which we don't want everybody connected to everyone else. We want some portion of them connected to everyone else. And this is what the GWESP term does for us. The geometrically weighted part of the edgewise shared partners is telling us that the marginal return to each additional triad diminishes as we get more and more of them. All right, that was the world's fastest introduction to these models. A variant of these models is called the latent space model, which says that instead of having an observed statistic for this logit model, instead what you have is a difference, a distance in some underlying hypothetical space, where that space is specified such that two nodes that are close to each other are likely to be friends, and two nodes that are far apart are not likely to be friends. And so you can fit those models as well. And the beauty of them is that they allow you to have essentially no basic hypothesis about what's driving similarity. It's just that we're going to find the best similarity surface that fits your underlying graph. The final class of models in this set are called the AMEN models, or the additive and multiplicative effects models. And this is by Peter Hoff and Alex Wolfowski. And these models do exactly what I told you before. You have row effects, column effects, and dyad effects. But then you also add this thing in here at the end, or you can add this thing called the latent multiplicative covariance. And this is a way of adding different types of latent spaces to the exact same model. And so this is the most general form of all these other models that I've talked about thus far. All right, that was by far the fastest that I've ever done this, and I've left all of 4 minutes for people to ask questions. So with that said, are there any questions or things that I just completely screwed up that someone wants to like either clarify or correct?
I actually gonna bring up the question that was asked last session again.
Please.
Is there like a general way of thinking about what's the size of networks in relationship to the amount of variables needed? Is there like a way of thinking about that? Which I think is sort of what Sinfei 2 was asking. But if that's the different question, you should unmute it.
No, I think that's that's not me to judge, I guess. But so I think that the short answer is that you have. I'm going to go back to where I was before. There's nothing mathematically constraining that says that you can't add parameters. I mean, the P1 model has 2 times n parameters plus 1 for reciprocity, right? So in that case, on n nodes, but remember you have n squared observations because you have it's essentially the number of observations you have on the it's the number of dyads you have. So the limit in terms of the number of variables and such you add to the model is really constrained by interpretability, and I think that we all appreciate parsimonious models. So for my thinking, and this is a substantive answer, not a mathematical answer, is that really the way you specify your model depends really strongly on the kind of question you have. If what you're interested in is one particular feature of the model, but you want to have a model that fits reasonably well, and you really care about, what I really care about is political homophily. But I suspect that there's geographic effects and income effects and race effects, all other things that are leading into it. I could go ahead and specify all those effects, or I could specify a latent space model and not worry about it. And so if I don't really care about a lot of the things that are driving the underlying network, but I want to test really well one part of the network, one substantive hypothesis, then I will often recommend using a latent space model because it doesn't require as much of the investigator in terms of to get a good model specification. If instead I want to know whether or not transitivity is higher in all Black schools than in all white schools, that is whether or not we expect social balance effects to be stronger in one setting than another, and I really care about the network generating process, then I'm probably going to go down the ERGM route and try to specify that directly and do the work that it takes to get a good fit. And so, but to me, that's just that's just been a matter of practice. I think that the beauty of the latent space models is that you can generally have a more parsimonious model and focus in on the substantive elements we usually care about. The ergo models can often get quite unruly as they get really big. But you essentially get a lot more control over what kind of features. And the thing you give up with the latent space model is interpretability. Often the pieces that are in the latent space are just generalized similarity, and what that actually means is unknowable. Does other people with experience have different opinions or echo that opinion? Did that answer the question, or did I answer a different question?
If we still have some time for more questions, there
Please.
are more.
Please do. Yeah, throw them out.
There's two. There's Faye had another question asking, can you talk about the difference between ergm and egocentric ergms?
Yes. So an egocentric ergm, for those that don't know, is that you can estimate the probability of ties between different types of egos and alters from an ego network sample. And an ego network, to remind everyone, is usually a set of independent samples of local networks. You've sampled a person, you've asked them about their relations, and they report on the characteristics of those relations. That gives you a clustered but unbiased sample of edges between egos and alters, practically. Whether or not it gives you any information on the ties amongst alters depends on the survey design, and whether or not that is informative of the structure of the network is a really difficult question, one that Tyler McCormick's presentation actually on partial data collection nicely summarizes. So I hope you get a chance to look at that. But what the ego network survey will let you do is compare the characteristics of the ego and the alter, and then generalize from that a sample based on row and column categories. And so it gives you these homophily effects that you could estimate. And the beauty of that is you could then simulate from that based on those attributes. I believe, and someone who, and David, you might know, or Tyler, if you popped in yet, might know, I think Pavel is working on a version of the ergm that will let you, or the ego version of the ergm, that will let you incorporate alter tie information to capture some of that extra density and some of that propensity for closed triad as reported by ego. But by and large, that's a much more difficult problem. So I think the thing is that under the hood, they're the same model. The data support that's underneath them is a little bit different. And the main issue is that you can focus on node match kind of characteristics fairly easily, but it's quite difficult to do pattern features. Maybe reciprocity, but I don't remember. I haven't looked at that recently. Does anybody else know if I'm accurate or if I've messed that up?
Jim, this is Dave. That sounded good, and I think you're right. Pavel and others are working on the sort of alter ties, and I guess I would just add, you go back to something you said all along, Jim, which is the key in ergms is model specification. And with certain specifications of models, you actually can estimate the statistics you find important from ego surveys. And because your model for the entire network depends on the statistics that you write down as being important, if those statistics are estimable from an ego survey, then for free, basically, you are able to talk about the entire network from an ego survey.
Yeah, and that's one of the magic things, right? I mean, it almost seems remarkable because we spent so much time and effort in the early 80s on investing in collecting global network data to estimate things that in the end of the day, we could have done better and more cheaply with ego networks. And so like homophily and degree are probably 85% of most of the structure of most networks. Add into that, geospatial and opportunity mixing, and you get a lot of stuff out of some very easy to collect local data. When you start asking questions about global hierarchies and between group bridging and things like this, it gets a little bit harder. But yeah, the ability to simulate global networks from local networks is something that is kind of remarkable, and this framework makes that possible. All right, I think we are a little. I wrote my times down. Let's see. So it's 13:55. Where are we at? All right, so we are a little over time. but we had a longer break schedule for this section anyway, so we're okay on that front. So I'm happy to keep yammering if people want, and we can still get back on schedule at 2:05. So what was the second question? Elaborate a bit more on what row effects, column effects mean, and give an example. Yeah, so a classic row effect would be, when I refer to row and column, what I'm referring to is the rows and columns of the adjacency matrix. Now, usually you don't have the adjacency matrix because that's ridiculous to store for big networks. But what it means, logically, it's nice to think that way, because if this is our adjacency matrix here, right, we can think of each person as a sender, each person as a receiver, and we can then ask ourselves, is there some systematic characteristic of senders that means you're more likely to see a tie in their row as opposed to a different row? And a classic example would be, men giving advice more often than women. So if the mansplaining thing is true, which it seems to be, then, in any given instance of people giving advice, it's some man yammering on, right? So this notion that a row effect of sending would be, gender as a row effect would be a sender effect. Gender as a receiving effect, that is, who's more likely to get advice from someone else, that would be a column effect. Now, row and column effects only matter in directed networks. They're only distinguishable in directed networks. In undirected networks, you have node effects. So it might be the case that men are more engaged in relations than women. And so that would be a node effect, but the distinction between row and column is irrelevant in undirected networks. And a dyadic feature is anything that dyads share. And so it could be, the obvious examples are homophily. So both actors are white, both actors are male, both actors are, something. The other kinds of dyadic features, they need not be functions of attributes. It could be that we both have prior experiences that are unique to us. So the fact that we both visited the University of Washington once, or we both, read a novel or anything like this, could be things that characterize dyadics. One of the strongest predictors for using a dyadic model comes with some complications, but you can use them, are other relations. So it might be that at the advice-giving network depends on the friendship network, that I only ask advice because I'm an arrogant SOB. I only ask advice of people I really trust. Because I don't want to look like a fool or something, right? So that would be a case where one network is a function of another network. And the nice thing about that is that's a dyadic specific feature. There's some technical distinctions within the ERGM package, the way it's specified, that are different from the substantive one, that distinguishes an edge effect from a dyad effect. And that's features that affect the presence of a tie versus the I always mess this up. So a feature that has to do with the characteristics of the dyad versus the characteristics of a prior edge. Is that right, Dave? Did I get that right?
Yes.
Yes, thank you. One of the things is a little bit, it does take a bit of time, and I'm sorry there's no easy way for me to give you a rubric for this other than to send you to the documentation, is that there is, because the kinds of statistics you can write down on the graph are so varied, it's a fairly technical language that distinguishes between person effects, sender effects, receiver effects, directed effects versus undirected effects, multi-relational effects versus not, and so forth. So there are lots of ways to do this. Now I think we should wrap up for a second before we come back in for the ABM set, just to give me a chance to take a quick break here. But the one thing I will note is that all of the discussion I've given thus far have been on binary networks. It turns out that that's not the limit for doing exponential random graph models. So you can do exponential random graph models on valued networks, easier on integers or things that can be turned into integers. And also you can do them on temporal networks, right? So I can predict future networks with past networks. And so that's a temporal ERGM. But you can also do a version of an ERGM which allows you to distinguish the start of a relationship from the end of a relation, which are called a stergm. And so these models allow you to distinguish relationships that churn and come and go. And I really love these models, particularly for those of us that are studying HIV or other kinds of sexually transmitted diseases, because the things that might lead to the start of a relationship could be different than things that lead to the end of a relationship. And so these models can be, you can model them separately. So it's a separated temporal ergm is what the STERGM stands for. And so we have 2 different models for each. I'm assuming that it's possible to do that one could generalize those to latent space models in the same way. I haven't seen those models, but I'm also going to be honest and say I haven't looked for those models. I'm not going to say they're not there. But the class of models that can be done are really quite broad. And so I encourage you to not think that you're limited to just what's in front of you. Moreover, the nice thing about the StatNet package is that if you want to, anything you can write down as as this change statistic, as a statistic on the graph, you can turn into an ERGM parameter. And so if you have a very specialized thing that you want to test, you can put it in this model, and you just have to write that function yourself. That's sometimes easy and sometimes difficult. We've done it we were very interested in some functions of triads in a paper that we've used for high school networks. And so we meaning Jeff Smith, took the effort and time to write the actual ERGM code to do the underlying change statistic code to make that happen. But that is possible, and that's the beauty of open source, is that all of us can add to this if it's something you want to do. All right, let's take a quick break. We'll try to come back. Let's come back at 14:10. So let's come back in 9 minutes, and we will. So instead of 2:05, we'll come back at 2:10, and that'll give me just a second to grab another soda and get my voice back in shape, and we'll start again.